if you come to Spain for any event, let us know, and we'd be happy to have you here in Teruel for a few days.
Will do.
You can give an introduction to the Signals project and what you're doing. It's a nice, tiny, cute city. I love it. Yeah.
Okay, let's wait 1 more minute and then we start.
Still coming.
Okay, I think we can start already. So welcome to the seminar, and thank you for coming in a unusual time, and thank you, Ray, for doing the seminar early in the morning. So today we have Ray Garner. He's a postdoctoral researcher at the Texas A&M University, and recently he did his PhD thesis at Cape Western Reserve University in Cleveland. And today he's going to give us a talk about narrowband imaging applied to M101 to derive stellar age pattern across the disk of this galaxy. So thank you very much, Ray. Whenever you want, it's all yours.
All right. Thank you very much. Can everyone see that? Thumbs up?
Yes, we see it nicely.
Well, thank you all for having me. And thank you for putting it at a weird time for y'all. I think your normal time would have been 3 in the morning here. So this is way better for me personally than waking up at 3 in the morning. Today I'm going to talk about the last chapter of my PhD thesis, looking at M101, the pinwheel galaxy, and using narrowband images to investigate the stellar age patterns across the entire disk of M101, and using that to say something about the spiral structure of M101. I want to point out that although currently I'm a postdoc at Texas A&M University, this was done during my PhD thesis at Case Western Reserve University with my advisor, Chris Mihos, and our resident telescope operator, Paul Harding. And in fact, this paper also utilized the help of my own father, Chuck Garner, who's a high school math teacher at the Rockdale Magnet School for Science and Technology, which was in fact my high school. So I'll point out what he helped me on as we go through. But to get us started thinking big picture, we have this theory of inside-out galaxy formation. And it does a lot of work to explain our observations of spiral galaxies. It explains that the inner regions are older, redder, more metal-rich than the outer regions, which are comparatively bluer, younger, more metal-poor. However, this theory, while it does explain a whole wealth of observations, it implicitly assumes that these spiral galaxies are evolving independently of each other, which, of course, we simply know is not the case. We see galaxies interacting with each other all throughout history, all throughout cosmic time. So an idea that I wanted to investigate throughout my entire thesis was, how do interactions potentially screw up this lovely picture we have of spiral galaxy formation? And a great local universe galaxy to look at that is with M101, the Pinwheel Galaxy. Fun fact, Charles Messier did not discover this galaxy. It was actually his collaborator, Pierre Méchain. So at least the M is still true. It still is M101, just not for Messier. When you look at M101, you see a nice, beautiful spiral galaxy. You see the nice blue star-forming arms. You see pockets of ionized hydrogen showing up in red in this image where stars are actively being formed. You see dust lanes. But the more that you look at this galaxy and the more that you compare it to other spiral galaxies that you might know and love, you notice that M101 is kind of weird. It's got this asymmetry to it. In particular, it has this asymmetric arm, what I call in my head very lovingly, its big wonky arm. And for decades, this big wonky arm has been used as evidence that M101 has undergone an interaction in its past. However, when we zoom out from this image and look at the M101 group as a whole, there is nothing there. This picture contains the entire M101 group. There are only a small handful of galaxies here. Let me introduce them to you. So, of course, these 4 galaxies are the only ones in the M101 group. Of course, we have M101 here in the middle. It's at a distance of just under 7 megaparsecs, slightly bigger than our own Milky Way galaxy. And then it has a whole host of small satellites. Some of them are ultra-diffuse galaxies and too small, too faint to be seen in this image. But we've got the 3 important ones here. To the right, in the west of this image, is Holmberg 4, a sort of Magellanic dwarf galaxy. It was in none of our narrowband images. Our images did not cover this galaxy, so this is the last time I'm going to mention that one. But the 2 more important galaxies, in my opinion, are right here to the east, 5477, a small dwarf irregular galaxy. You can almost count the number of stars in this galaxy. But it is right next to M101, not that far separated. And then to the south, we have 5474. This is the most massive companion, but still it is a dwarf spiral galaxy. However, it is also interesting. It is a peculiar spiral because its bulge is off-center from its disk. I got some thoughts on that. I'd be happy to talk about that later. And then there's a few background galaxies in this image as well. But that's essentially the entire M101 group. So, you know, what the hell happened to M101? Who interacted with it? And it's not just in the optical where we see that M101 has interaction tidal features, but we see this across tons of multi-wavelength data sets. So for instance, here in this optical image, this is a deep B band that my advisor, Chris Mijos, took back in 2013. Here you can see some low surface brightness extensions to the northeast and east, labeled here the northeast plume and the eastern spur. Chris was able to get some Hubble photometry of the northeast plume, and the stellar populations there are consistent with the star formation burst around 300 to 400 million years ago. So that's the time scale of the interaction we're talking about, just a few 100 million years ago. When we look in the ultraviolet, we see that M101 has what is known as a type 1 extended UV disk, or an XUV disk. These galaxies have star formation happening beyond the radius that we would think star formation should have stopped due to low densities. And when we look at other type 1 galaxies, they are all galaxies that are undergoing interaction. So this is also suggestive of an interaction. And even when we look at the radio, the neutral hydrogen, we see that there is asymmetry in the hydrogen gas. Here, actually, in the opposite direction to the northeast plume. Instead of pointing to the northeast, it's pointing towards the southwest, marked here by the letter P. And there's even a bridge of intermediate velocity hydrogen gas between M101 and its largest satellite, 5474. So all of these pieces of evidence have usually been put together to propose that at some point in the past, M101 was essentially whacked by 5474. And a simulation was only recently done back in 2022 by Sean Linden and Chris Mijos, showing that 5474 and M101 interacted, according to the simulation, around 200 million years ago. And it accurately reproduces the current features we see of M101, and of course, we can see what M101 will look like far into the future. So we've got a simulation, we've got all these pieces of evidence that M101 has gone through an interaction. Now the job for me as an observationalist is to ask, how did this interaction screw up the normal properties of a spiral galaxy for M101? So to do this, we have some narrowband data taken at Case Western's 24-36-inch Burrell Schmidt Telescope out in Kitt Peak, Arizona in the southwestern United States. We've got narrowband filters targeting 4 key emission lines. We've got H alpha. That's nothing special. Everyone has an H alpha filter. H beta, fewer people have an H beta filter, but it's still relatively common. We have an O3 doublet, 4959 and 5007. That is less common. And then what's really impressive is we have a filter covering the O2 doublet at 3727, and hardly anyone has that. So we've got an amazing set of narrowband filters sitting on these emission lines, but we've also got narrowband filters measuring the adjacent stellar continuum to each of these emission lines. So in total, we have 8 narrowband filters. You can see 2 of the examples here are H alpha on and off band. Of course, in the on band, you can see all the bright pockets of star formation throughout M101 and the 2 satellite galaxies. And then in the off band, you can see it's comparatively dimmer, although obviously still present. The galaxy is still emitting light at those wavelengths. And so, as I'm sure you all know with the J+ survey, you can do on minus off band and get some great continuum subtracted. And because we have narrowband filters looking at the continuum as well, we have not only deep, but very accurate continuum subtracted images. And here they are. H alpha, H beta, O3, and O2. And you can see all the beautiful H2 regions lighting up. You can see some darkness in these images, which I'll talk about in a moment. And I'll point out that these are not our full images. Our full images measure about 2.5 degrees on each side. So we're truly getting wide field images to investigate the entire M101 group. Now, before I talk to y'all about this most recent paper of mine, I do want to point out some of the work that our little group has already done. We've only published a handful of papers. The first one was back in 2017. Aaron Watkins, who was the PhD student who came before me, looked at H alpha to UV flux ratios throughout the entire M101 group to look at star formation in different environments. And then, he graduated and I came in and started my thesis entirely focusing on M101 in this narrowband data set. My first paper was looking for any outlying intragroup star formation. If M101 went through an interaction, maybe there's tidal debris. Maybe we can find that tidal debris in our narrowband data. Spoiler alert, we found literally only one example of debris, one small little H2 region. So check out that paper. The paper I'm most proud of is this one, looking at strong line abundances of over 720 H2 regions throughout the entire group. This makes it the largest abundance sample for M101 in the literature to date, although that will probably soon change. And I showed that M101, its abundance gradient might actually plateau. It might flatten in the outskirts. And, interpret that. What does that mean for M101's evolution? The paper I'm about to talk to you about stellar age patterns across the disk of M101. It has been accepted to AppJ. It's currently on archive. And in fact, I just sent AppJ back the proofs, so it should officially be published any day now. And then another paper that's in the works, using the H alpha and H beta images to look at different star formation rate indicators between the H2 regions and the diffuse ionized gas in the M101 group. That is a work in progress. But let's go back to the stellar populations here. And I'd be happy to talk to you about any of these papers later. So how can we get stellar ages out of our narrowband photometry? Well, let's go back to our H beta and our O2 images. I mentioned there's some darkness in those images, and you can really see it now. Where aside from the brightly lit H2 regions, there is that darkness sort of following the spiral arms. I want to stress that this is not bad over subtraction. We did all the data reduction properly. We are actually measuring here stellar absorption features in the disk of M101. And so you could, as many people have done in the past, you could calculate equivalent widths through these filters and see how they change radially. Those equivalent widths should vary as a function of age. And so we can essentially get a radial age gradient out of our data. And that's exactly what I have for you here. The top plot is the H beta equivalent width as a function of radius. And you can see that it decreases to about 10 kiloparsecs and then plateaus. The bottom plot is our O2 equivalent width. And of course, now we've got to switch up some nomenclature because there are no O2 absorption lines. So instead of saying O2 equivalent width, I'm going to say 3746 equivalent width for the central wavelength of our filter. You can see that equivalent width decreases to about 5 kiloparsecs and then plateaus. So the H beta equivalent width is pretty easy to interpret. We are measuring an increase in age as we go further out towards the galaxy. Or sorry, yeah, more younger stars as we go out further out in the galaxy. But what the hell is happening in that 3746 filter? So we had to understand what we were actually measuring here. And so we used Seagal, which is commonly used as an SED modeling, as an SED fitting tool. You know, give it a bunch of multi-wavelength photometry and it gives you an SED. Here we used it as a modeling tool. Give it some assumptions about the star formation history, the amount of dust in the galaxy, the metallicity of the stellar population, and just give us an SED based off of that. Don't fit anything to it. And that's what you see here. So these are all single burst populations. Young ages at the top, 1 mega year in this in this black purple, all the way down to essentially the age of the universe, 13 gigayears in this dark red here at the bottom. I'll start over at the right, where I've zoomed in on the H beta wavelengths. Our on band is shown by the dark orange rectangle, off band by the light orange. And you can see in our on band, we really are only measuring H beta. We truly are just measuring one single line. And that line changes with age as we would expect it to. Remember, at early ages where there's O and B stars, which have weak Balmer lines, so the H beta absorption will be weak. Then it gets deeper as those O and B stars die out, leaving just the A and F stars, which have the strongest Balmer lines in their continuum, until about 400, 500, 600 mega years, somewhere around that time scale, where they start to die out, leaving behind the G, K, and M stars, which have weaker Balmer lines and start to have molecular or metallic lines in their spectra. And you can see that we aren't measuring anything else in our off band. So when we do on minus off to calculate an equivalent width, we are truly just doing H beta. That is not the case for our O2 filters, where here the on band is dark green, the off band is light green. Here, we're not measuring O2. There are no nebular emission lines in our models, and we're masking the H2 regions in our data. But what we are measuring is a bunch of those higher order Balmer lines all at once. In addition, we're also sensitive to the slope of the continuum in this blue region. It's a very messy region of the spectrum. And so, as we do on minus off, those are going to change with age in a complicated way. And as we get to very older ages, we actually start to measure a cyanogen line in our off band, and that's going to screw with our age measurements as well. So we need to use the two of these together to get good age estimates out of them. And so we can explore how these two equivalent widths vary together as a function of age by looking at diagnostic equivalent width plots. Now, in my head, and Chris didn't let me put it in the paper, even though I wanted to, in my head, all of these tracks and these plots look like unbent paper clips. So in my head, I call them paperclip plots. So if you hear me say that, that's what I mean. I mean these diagnostic plots. So once again, we're just using Segal as a model generator, not to actually fit any photometry, just to generate some models. And you can see we explored primarily 4 different parameters with Segal. These are exponential star-forming histories characterized by the E-folding timescale tau, with an optional secondary burst of star formation. So the top left shows the variation with different E-folding timescales. So the different colored lines are these different taus. Yellow is 500 megayears, characteristic of, say, an elliptical galaxy. Dark red is 30 gigayears, characteristic of a spiral galaxy. And you can see they show the same sort of properties. That at early ages, we have relatively deep H beta and 3746 equivalent width. But those get deeper as you go on. Those O and B stars die out, leaving the A and F stars. Those A and F stars then die out, weakening both of those lines and pushing it up towards the top right. You might notice that our 3746 line starts to go above 0, sort of like pseudo emission. Once again, I want to stress there are no emission lines in these models. Remember, this is caused by a cyanogen feature in our off band. So as we do on minus off, that creates some pseudo emission, but it's not true emission. We looked at our sensitivity to stellar metallicity. M101 is roughly solar metallicity, so we don't expect to see huge change. And indeed, there's not much change in these diagnostic plots. We looked at an optional secondary burst, where the effect of that is to take, for example, this older prong and bend it inwards towards the younger prong. We start to fill in the space between these two prongs with a secondary burst. And then, of course, we also had to look at our effects of dust. M101 is not a dusty galaxy, so we're not too terribly worried about the effects of dust. And you can see it doesn't change much in those models either. So really, what we are sensitive to is the actual parameters of the star formation history, the E-folding timescale, and if there was a recent burst. So now that we understand how our data can measure stellar populations, let's actually see what we're trying to answer. So I've already shown you the radial age gradient, or one way to measure it for M101. But the problem is M101 is a spiral galaxy, and you would naively believe that spiral arms should mess up that radial gradient. This is what is known as the large-scale shock scenario. So it goes like this. When gas enters a spiral arm, that gas should be shocked and collapsed under this new gravitational potential to form stars. And then those stars will continue moving along in their orbits, moving out of the spiral arm. And that should result in an age gradient, where near the spiral arm, where those O and B stars are, it should still be dominated by young stars. But as we move into the interarm region, those young stars have died out, leaving behind a relatively older population. Now, numerous simulations do support this scenario, especially in galaxies with bars or a constant pattern speed, but this is very hard to observationally measure. only in recent years, and I'll point out the work by Martinez Garcia, 2009, 2011, and 2015, where they've been able to do this using a combination of optical and infrared photometry. But it's very hard to do it with just optical because of the age metallicity degeneracy. So let's see if we could do it. So we need to define some environments. So let's do that. We will define the inner disk of M101, just based on where it's hard to define spiral arms. This is about less than 4 kiloparsecs. Then we'll define the spiral arms. So we will fit logarithmic spirals to our deep B-band image to find where the spirals are. You can see sort of a process, our process in this image here, and then use the H-alpha image to determine the width of the spiral arms. And then obviously the interarm is anything that isn't a spiral arm. This is actually the part that my dad helped me out on. I was having a little trouble with the math of logarithmic spiral arms. He was able to help me out. And then for signal to noise regions, we will make a distinction between what we're calling the main and the outer disk of M101, split at around 15 kiloparsecs. Where in the main disk, we will bin our pixels in 9x9 bins to build up that signal. And the outer disk, we will pick a few particular regions of good signal and bin them in 40x40 pixels. I want to stress that what we're calling our main disk is usually what people refer to as the full disk of M101. So we are going out much further in our data than other people have in the past. So now that we've got our environments defined, let's see where all this data lies in our diagnostic equivalent width plots. So first, here's just all of the data for the main disk, colored by radius, and you can see one of our model tracks overlaid on top. First of all, we get the expected age gradient back. The purple regions, the regions that are low radius very near the center, lie along the older prong between, about 5 gigayears old, according to these models. Meanwhile, as we go out in radius towards the light green and yellow, we move towards the younger prong. However, obviously, these points are not tightly clustered around the model prongs. Remember that we're also sensitive to a recent burst in these models that fill in the gap between these two prongs. So we believe that all we're seeing here is just normal stochastic star formation, typical of a spiral galaxy.
Sorry, Ray.
Yeah.
These points are the binned pixels?
Yes, they are.
Okay, it's so separate like square bins, and then you've done this measurement on those bins on the
Yes. Yes.
Okay, thank you.
And just so you know, I'm not hiding anything. We can also make larger radial bins, and you can see we are getting a nice transition in ages from near the center moving outwards. So I'm not hiding points behind other points. But now let's look at those morphological environments and see where they fall on these diagnostic plots. Here we've got the inner disk in red, the arms in blue, and the interarm regions in green. We see, once again, the radial trend is still present here. The inner disk is generally older than the spiral arms and the interarm regions. But the interarm regions aren't all the same age. It's mixed in ages. There is a young population similar to the spiral arms, and an older population similar to the central region. So let's make a spectral selection. We could take what's in these two boxes. We've got one on top of the older interarm regions and one on top of the younger interarm regions, and take whatever's in these boxes and see where they are spatially. So take whatever these boxes and plot their XY positions. And this is what we have. So on the right now is an XY plot. The light blue is our spiral arm masks. The blue points are those that fall in the spiral arm. Green points are the true older interarm regions, and the purple points are the younger like arm interarm regions. And when we look at this spatial plot, we see that the like arm, the younger interarm regions, are preferentially, there are a few exceptions, but preferentially found on the outer edge of a spiral arm, while the older interarm regions are found preferentially along the inner edge of a spiral arm. We believe that this is the age gradient across a spiral arm, fully in line with what the large-scale shock scenario says should be happening. And so our success in detecting this, remember, we're not using any infrared or ultraviolet photometry to help us do this. Our success here probably lies with our relative insensitivity to dust, and M101 is not dusty, and the fact that we're measuring multiple spectral features at once. We're not just looking at, say, an H beta and a magnesium line. We're looking at a bunch of things all at once. But you might ask, this made a spectral selection and plot it spatially. We can also do the opposite. We can make a spatial selection and see what the equivalent widths are. And so that's what I've done here. I've selected 3 boxes across the spiral arms and looked at their H beta equivalent width, since that's easier to interpret than the 3746 equivalent widths. So in each of these boxes, where 0 marks the middle of the spiral arm, you can see that on one side of the spiral arm, it drops, indicating the presence of younger stars, those A and F stars that have recently been formed. And on the other side of the spiral arm, it's of relatively low equivalent width, suggesting older, much older populations. So still here, we are seeing the evidence of the large-scale shock scenario, where we're getting a changing age gradient across spiral arms. So this was the main disk. Now let's look at the outer disk, beyond 15 kiloparsecs. So remember, in the outer disk, we're doing it in much larger bin pixels, and we're picking a few different regions. So you can see my little map here on the left. We've picked a few pairs of regions labeled A and B. A's are along the outer edge of a spiral arm. B's are along the inner edge of a spiral arm. And then a few other regions sporadically throughout. We tried to target specific features while also remaining azimuthally unbiased. So we've got a few, like, deep interarm regions along some spurs near stellar your star-forming regions throughout. And you can see where those different pixels lie on our diagnostic plot, where the inner edge along an arm is colored in red, the outer edge along an arm is covered in blue, and anywhere else is gray. And there are a few key conclusions we can make from this plot. So first of all, we've got a much stronger absorption here in the outer disk than we had in the inner disk. This means that there's a much more dominant younger population here than in the main disk. We also see that there are populations more consistent with a fading or a near constant star formation history out here. And when we look at the populations near the northeast plume, which are labeled 1 and 2 A and B here, I think, we get populations that have a young, but, an old but not dominant population underneath, which is similar to what Chris saw in his Hubble photometry of the northeast plume. But the main interesting point here is that the inside of the spiral arms, the red regions, by and large, are older than the outside of a spiral arms, colored here in blue. This is the same trend we saw in the main disk. This is a problem because, according to the large-scale shock scenario, that trend should flip outside of corotation. We should see that the inside of spiral arms are younger than the outside of spiral arms, which are older. That's not what we see. And we are well beyond corotation. The corotation for M101 is usually taken to be around 15 kiloparsecs. So these trends should be flipped. We should be seeing different things than what we're seeing here. So how do we rectify this? Well, there are 2 potential solutions. The first one is that star formations in M101 simply isn't governed by the large-scale shock scenario. There's been a lot of debate in the literature about how important spiral arms are to the overall star formation of a spiral galaxy. In particular, I will point out FOIL 2010 and 2011. where they show some pretty key evidence that the interarm regions of spiral galaxies are equally as efficient at forming stars as spiral arms. However, I don't believe that is the case for M101. A different group, Cedrus 2013, found that M101's spiral arms are 30 times more efficient at forming stars than its interarm regions. So I do not believe that this is the case for M101, that it is not governed by large-scale shock scenario. So that requires us to adopt the other explanation, that there are multiple pattern speeds and thus multiple co-rotation radii for M101. If there are multiple co-rotation radii, then we're never outside of a co-rotation. So we're never going to see that trend flip. But of course, is there actually multiple pattern speeds for M101? Well, back in 2009, Sharon Van Mate and her team found multiple pattern speeds for M101 using high-quality H1 and CO data cubes. And here you can see there are 3 different pattern speeds over these different radii, giving different co-rotation radii. So if there are truly multiple pattern speeds, then like I said, we wouldn't see a flipping of the large-scale shock pattern until outside the largest co-rotation radius, which at least in our data might be beyond 25.5 kiloparsecs. That's our largest radial point, although it's larger than what they were able to do in their data. The problem with having multiple pattern speeds is that suddenly we've got to toss out everyone's favorite quasi-static density wave theory of spiral arms. We have to adopt dynamic or transient spiral arms instead for M101. But there are benefits to this, consequences for M101's evolution. So when it comes to the benefits of dynamic arms, first let me just remind you what those are. These are spiral arms that appear and reappear in cycles. So they are short-lived, but because they keep breaking up into segments and reconnecting, they appear to be long-lived. There will always be a spiral pattern, even though any particular spiral pattern will be short-lived. So they do form these large-scale patterns that we see in spiral galaxies. This has a consequence that means that these multiple pattern speeds have to be supported and linked by something called mode coupling, where different resonances of different spiral patterns overlap. So for instance, perhaps the outer Lindblad resonance of an inner pattern overlaps with, say, the co-rotation resonance of an outer pattern. And that will help link these spiral patterns and build it up at large radii, giving us these large grand design spirals that we see, with spiral features extending to large radii. However, a consequence of mode coupling, at least in simulations, is that it stimulates the production of one-armed spirals, which is sort of what we see in M101. Remember, it has that big wonky arm. So if M101 has transient spiral arms, then it is already ready and willing to produce a single arm spiral and maybe just needs a push to do that. Well, that push could be caused by the interaction it had with 5474. This has consequences for the simulation that I showed at the beginning. There, Sean Linden had to up the mass, had to artificially increase the mass of 5474 to reproduce the observed features of M101. But if M101 is already willing to produce spiral arms because of this transient spiral pattern, willing to reproduce the single arm, the asymmetric arm, because of this transient spiral pattern, then the simulation, we can lower the mass of 5474 to make it more in line with observations and still reproduce all the features that we see. So that was pretty much the entire paper here. I'll end with just a little brief summary. So using our narrowband data, we were able to recover the radial age gradient that other authors have found for M101, but also found those age gradients across spiral arms, consistent with the large-scale shock scenario in the main disk. Remember, unexpectedly, we found that same trend still existing in the outer disk, which requires us to adopt transient spiral arms, which has consequences for the previous evolution of M101. And it also really does provide some constraints for ongoing spiral arm simulations. Those simulations, when they try to reproduce the large-scale shock scenario, typically can only do it with flocculent galaxies with short, stubby little spiral arms, but struggle to reproduce grand design spiral galaxies like M101. So clearly, there's some more work needs to be done by the simulators in those simulations. So that is where I will end, and I'd be happy to take as many questions as we have time for. Thank you.
Thank you very much, Ray. So is there any questions? Yes, Elena?
Please. Okay. What is the surface brightness depth of this H-alpha image of this galaxy?
What is the surface brightness of the entire galaxy?
No, the outer disk. The depth of the.
We are. The only number I know off the top of my head, remember we made the cut between the main and the outer disk. That cut comes down to about 23.5 magnitudes per square arc second, I believe.
And did you check the, like, it is this galaxy classified as XUV disk, XUV type 1 disk galaxy, right? So
yes.
did you check the, like, the disk size with the UV and with this H-alpha, with this depth?
Not in this project, but I have looked at that before. I don't think it's made it into any papers, but the extent of the H-alpha disk pretty well covers the extent of the UV disk.
So it's like it could cover the same level as
yes.
UV.
Yeah.
Okay. And what was the exposure of this H-alpha exposure time?
The exposures, so each individual image is 1200 seconds, but for example, the H-alpha image is actually like 72 exposures stacked on top of each other. So almost 24 hours in total.
Oh, I see.
And that's pretty similar across all the other images as well, around 18 to 24 hours in total exposure.
Okay, thank you.
Yeah, Elena? Yeah.
Yeah, thank you. This was a very, very nice talk. I really enjoyed it. It's a very interesting work. I was wondering, is there any reason why you use equivalent width rather than more classical leak indices?
I don't think there's any particular reason other than, that was easy for us to calculate with our flux data. And it is what, when other people have investigated, say, H beta strength as a function of age, most everyone else has calculated equivalent width for H beta as a function of age. So in order to compare our work with others, we needed to do equivalent width.
Okay. And do you have enough, do you have other photometric bands to do an SD fitting, or you only have the narrow bands?
We have the narrow band. We also have broadband B and V. But that's all of our data from our own telescope. There is an ESA project called Dustpedia that has M101 across from far UV all the way into Herschel-Planck data. So I have all those images on my computer. And at one point, we did look at doing a whole like SED fitting for the entire disk of M101. But we ran into issues. Segal did not agree with our narrowband measurements, which we knew were correct. So we kind of dropped that project and moved on to other things. But there does exist multi-wavelength coverage of M101. It's out there. Just I don't think anyone's done much with it.
Yeah, I guess it's a problem of the spatial resolution, right? You're focusing on very small regions, so tracing that with the infrared, it's very difficult to cross-match.
Yeah. Yeah.
Sorry, can I?
Go on, go on.
So in the suggestion that this galaxy interacted with M101, do your stellar profiles or stellar age gradients are in agreement with that trajectory or with that simulation?
I don't think they are, but I don't think that's a problem because that interaction happened so recently ago. Remember, 300 mega years is the time scale for the interaction. That what we are really looking at, because we've masked all the H2 regions, all the areas of active star formation, we're really looking at the underlying older population of M101, which would, because of our masking choices, would not be as impacted by the interaction as the younger population. I did see evidence of that when I looked at the gas phase abundances of M101. I did see evidence that the interaction screwed with it, but not with these stellar population ages.
Okay, thank you.
Yeah.
Any more questions? So I have one question about the, you mentioned the part where some people had suggested that the star formation efficiency in the interarm region is equal to the arm. And I'm very curious what evidence they provide, because visually when we look at the UV or H alpha, we see that the arms are much more active and much more. So what evidence did they provide for that claim?
It was so most of it, if I'm remembering correctly, was based off of neutral gas and molecular gas, and when you look at that, some summed over areas, I believe what they were saying was that over areas, maybe the spiral arms are marginally better at forming stars, but they were still finding nice star forming properties in the interarm regions. I'd have to go back and look at those papers though.
Yeah. And about the masking of the H2 regions, how did you do that? Automatically or visually?
So it was all done programmatically using AstroPi segmentation modules. It's a Python version of and very similar to Sextractor.
Okay.
Just detecting above a certain pixel level has to be connected, all that stuff that Sextractor does. It's actually this what we used here in the stellar population is actually the inverted mask that we used in my gas phase abundance study, where we masked everything but the H2 region. So we just inverted it and looked at the stellar populations this way.
Okay. So later after the meeting, I'll send you an email about a new method that we have, and it's able to mask these clumps much more precisely, let's say, not based on a signal to noise threshold on the pixels. So hopefully that can be useful in studies like yours as well. We're using it here, and I'll send you the things later. Any more questions in the meeting? I had another question about you mentioned the scenario where you were trying to explain these arms. You mentioned them breaking and then and how having temporary arms between the things. But I wanted to see, is there any actual galaxies that show this scenario that you outlined? Can you visualize them with an existing other galaxy that is in that phase?
So
or is this purely based on simulations?
It's flocculent galaxies might be the best evidence, but as Selwood in 2011 pointed out, that it is very hard observationally to distinguish between different modes of spiral arm mechanisms. So far, aside from, I guess, my work and maybe Martinez Garcia, very little. It's still incredibly difficult to say that spiral galaxy is quasi-steady density waves. This spiral galaxy is transient arms. It's very hard to observationally say that. So far, it's pretty limited to just a distinction made in simulations.
Okay. Okay. Thank you. No
Mhm.
questions here. So just one more tiny question about the edge of spiral arms. How do you define that? So to define the limit of the edge of spiral arm.
So the location of the spiral arms was determined in our B-band image, but the width of the spiral arms was determined using our H-alpha continuum subtracted image, where we basically just wanted it to encompass most of the H-alpha light that one would associate with a spiral arm. It was done purely empirically. However, there was a small little fitting code that I devised, but essentially the widths came out to be 2 to 2.5 kiloparsecs across.
Okay. Okay, great. Thank you.
Can I ask a question about continuum subtraction? In those images, you told the dark region are not over subtraction; they are absorption region. And when I'm looking your paper, most of the stars have absorption in H beta. And did you do the PSF deconvolution in your images?
I am sure we did. I did not do any of the data reduction myself. That sounds like it's a question for my advisor, Chris Mijos. I didn't do any of the actual data reduction. I'm sure he did, though.
Thanks.
Yeah. Thank you. No other questions? Okay, so then we can finish the meeting. Thank you very much, Ray, for agreeing to come at this early morning in Texas. I hope it's becoming a better time now. Thank you. And,
no problem. Thank you for having me.
We'll be in touch. And thank you everyone for coming at this non-standard time. Okay, so have a good New Year and Christmas holidays. Yeah, we'll be in touch. So bye-bye.